Kindly wait, others let them finish. All right. I hope those who have joined at right time, they would have finished. So others can try it even later sometime. So good job, guys. Thank you. So I'll be just ending this. So how was it?
It was fun, sir.
All right. So it was just a revision of what all things we have discussed till now. All right. So yeah. So we'll continue with what we have done the other day. Yeah, Rekshak, I saw your question. So why are the common problems in RFIC design? I think the question is what are the major issues in RFIC design? And yeah, so major issues are non-linearity and noise.
Hello, sorry.
Sorry for the delay. Yeah, I'm seeing the chat box. So from where do I start? Yeah, the major issues are nonlinearity and noise, and whatever you speak like harmonics or whatever it is, all these are coming under that only, right? Because we discussed harmonics and other things as the effects of nonlinearity. So all those things are covered. Yeah, Vishnu, power is an issue actually, but when we look at major issues, we consider nonlinearity and noise as the major issues.
Yes, sir. I meant it that way. Like it's not major issue. We can
Oh, okay.
overcome it.
I thought you were asking me a question. Okay, harmonics is, yeah. Your point is right, Rakshak. At the same time, we treat this harmonics again under this non-linearity only, right? Okay, so we continue with what we discussed yesterday. We were looking at IP3 measurement. So we'll go back to the numerical what we discussed yesterday. So in this numerical, when we solved it, before that we have discussed two methods or two ways actually to measure IP3. So the first way is we have equated the amplitude of fundamental and IM3 terms, and we stated that you can see my screen, right? Oh, okay.
No, sir.
All right. No, I was presenting actually. Then what I was presenting? What can you see now?
Blank. Now we can see,
Okay.
sir.
So we discussed two methods to find IP3 point. Yeah, the first one is we equated the fundamental and the IM3 amplitude and we obtained IP3 using this formula under root of 4 by 3 alpha 1 by alpha 3. This is more treated as a shortcut method because if you look at this method, we are actually equating the intermodulation term with the fundamental term and thereby arriving at an expression for IIP3. But from the expression itself, we can think that this will definitely give a very high value because we are taking the amplitude which is making your fundamental component equal to the IM3 term. This is one method. Um, Again, I hope I mentioned that we are not considering we are considering this only up to third order nonlinear, so there will be some limitations. And the values what we are getting from these IP3 measurements, or I can say IP3 is actually not a directly measurable quantity. Rather, IP3 is generally obtained even in simulations. Also, it is generally obtained using some extrapolation or extrapolation way. The reason is because when I look for this high value of amplitude or when I look for this high value of IP3, the system would have been definitely undergone a heavy gain compression, or because of the power supply limitation, the system would have been compressed the gain to a higher extent. So most of the cases, the value which is given by the formula, especially when we use this formula, will be very high. And when I use that value to characterize nonlinearity, that will not make any direct sense. It will give the extreme value of if I use this formula. Then one more practical approach is actually to use the estimate method, what I have explained the other day. So there, what we have done is we have just taken the ratio of these two, the ratio of the fundamental component and the IM3 component, and then there we plugged in the already calculated IP3 formula. If you remember, this is what we have done, and then we arrived at this estimate value. So in this estimate value, we can arrive at the IP3 in the power level of IP3 from the difference between the output fundamental and output IM3, and from the input power calculation. So when I use both the formulas, both will not lead to the same result. So I forgot to mention that yesterday. In fact, I did not realize that yesterday. So this formula, when I use this calculation for IP3, and the other one, the shortcut method or the directly by equating and getting this formula, both will not result in the same IP3 value. The reason is both approaches itself are different. And second thing is, in the other case, we have actually taken the IP3 value is the amplitude we have taken by directly equating the fundamental and the third order harmonic. So both approaches are slightly different and both will not result in the same IP3 value. Now when we do designs, what should we do? So if you go with both the methods, then also you will arrive at an IP3 value. But we have to check that really with a system simulator, because we do not know whether at the value which we are getting from this IP3, whether the system will be the gain will be compressed so much or not. So if you remember, when I showed the simulation yesterday, in simulation we did not see any graphs of this kind. So in actual, if you plot the variation in actual form, it will be something like this. It will increase and then it will compress. Then both will be with different slopes. It will compress, and the other third order also will compress. Now these compression may happen at a very high value also, but these two will meet even at a very high value. But we can see that from after a particular point, after it crosses the 1 dB compression point, the system has compressed a lot. So in such cases, we use the method of actually extrapolation of these two, and where it meets, and this is considered as actually the IP3 value. So what I am concluding here is you can use both the methods, whether the estimate formula what we discussed yesterday, or the other value of IP3 what we derived on day before yesterday. But the values given by both are just estimate. And this is by using a simulator, we will look at the non-linearity and then we will arrive at a value. But so the underlying point is this IP3 is not a directly measurable quantity, and by having an estimate value of IP3, we can clearly understand, or we can clearly limit our input signal, because 1 dB compression point itself is another measure for that, right? So this IP3 comes again almost 9 dB plus this 1 dB compression point. So since this is not a directly measurable quantity, we generally use these two methods, and these two methods will result in slightly different answers, right? So if you ask me which is more accurate, this method will give you a value, what to say, which is this method will give you actually a lesser value comparatively, and this is a widely used, or this is the widely accepted method than the other one. But even in this, we have actually brought in the formula which was derived using the other method, right? This is a clarification for that. I hope yesterday very few were attending class, so I hope this is giving some clarity to that. If you want furthermore, we can actually, okay, we will discuss even at the end of the session, right? Okay, so just we will look at one more topic. So one announcement is we are actually about to finish our unit 1 with probably in another this week definitely we will finish unit 1. Okay, so we looked at non-linearity and we have seen the various performance, the effects of non-linearity and the performance metrics from that. So today we will see the effect of non-linearity in a cascaded stage. Because we know that in an RF system, signals will be definitely processed in a chain, or we do have cascaded systems there. So signals in an RF system are processed by cascaded stages. Since cascaded stages are there, we are giving an attempt to understand the non-linearity in a cascaded stage. So for our analysis purpose, I'm considering only 2 stages of cascade. Again, analytically, when we understand the non-linearity, we will use the same polynomial what we have taken before, and then we will process that using signals, right? So what I consider here is I'll consider two nonlinear stages which are in cascade. So the first stage this is the first nonlinear stage and this is the second nonlinear stage. So this is x of t, this is y1 of t, and this is y2 of t. So I mark this as y1 of t and y2 of t, and both are nonlinear. Right. Now, since I was using an expression like y of t, we were relating y of t to x of t as alpha naught plus alpha 1. So for this stage, we will use that variable. That variable we use alpha to express the fundamental gain and other to capture all the nonlinear effect. We'll use this term alpha, and for this stage, we will use the term beta. And finally, what we are looking at is we are looking at the IP3 of the cascade. When you have a cascaded stage, what will be your IP3? Now, the IP3 of this I will write it as IAP3 of 1, and the IP3 of this I will write as IAP3 of 2, second stage. Right. Now, again, like any other system, when you study, we will apply a two-tone test, say at omega 1 and omega 2. And we are looking at the output components. So when you give omega 1 and omega 2, we are looking at the output components. So let me start with y1 of t. So I can write y1 of t as all the terms with the first stage I'll write with alpha. So I'll write right from the fundamental. We can add alpha naught also. I'll write alpha 1 x of t plus alpha 2 x square t plus alpha 3 x cube t, again limiting to third order nonlinearity. And the second term y of t, the second stage output y2 of t can be written in terms of y1 of t. So I can write that as in terms of beta 1. So beta 1 into y1 of t plus beta 2 into y1 square t plus beta 3 into y1 cube t. Right. This is y2 of t. Now, in order to evaluate, so to evaluate IAP3, so we know that from the previous shortcut method, we have seen that to find IP3, we are looking at the first order term or the fundamental term and the third order intermodulation term. The same thing, so the same principle will extend. So to evaluate IAP3, we will consider only first order and third order terms. So to evaluate IAP3, we'll consider only first order and third order terms. So I have written y2 of t as beta 1 y1 of t, but y1 of t comes from the previous equation, right? So now I can write y2 of t as beta 1 into, in place of y1 of t, I have to actually substitute everything. Probably, I will do in this form. It is, so in place of y1 of t, I have to bring in this entire equation in all these terms. After that, if I expand that, I will get a set of terms, but from that I am considering only first order and third order terms. So I am writing only those terms here. So y2 of t can be written as alpha 1 beta 1 x of t. Maybe you can try by writing the entire expression for ones, and you can extract. Yeah, Rakshak DC term, yes, it can be considered. You can, in fact, you can write alpha naught. Even if I'm considering alpha naught, in order to evaluate IAP3, I will consider only first order and third order terms. That is the reason why I did not enter that DC term over there. Right, so alpha 1 beta 1 x of t plus this I am directly writing. Probably you can try this by just just plug in y1 of t in the second equation. So say this is equation 1 and this is equation 2. Plug in y1 of t here in each term, expand it, then you will get a lot of terms. From that, pick only the first order and third order terms. So I'll get alpha 3 beta 1 plus 2 beta 2 alpha 1 alpha 2 plus alpha 1 cube beta 3 into x cube of t. This is y2 of t. Right. Probably you'll be wondering about this term. So you can definitely try this. Write y2 of t after plugging this y1 of t here, and then write only the first and third order terms. So this is my y2 of t. The terms are there, but we are considering only these two. Yeah. So from this, we know that AIP3, we have written the formula before. It is 4 by 3 alpha 1 by alpha 3. This is AIP3. Now we will extend this for the cascaded stage. So in a cascaded stage, I can write this AIP3 as under root of 4 by 3. So alpha 1 denotes the terms. Alpha 1 is actually the coefficient of the first order term. So in this case, that first order term coefficient is not alpha 1, it is alpha 1 into beta 1. So I'll write that over there. Alpha 1 into beta 1 divided by alpha 3 is the third order coefficient. Here that term is this entire expression. So I'll write that alpha 3 beta 1 plus 2 alpha 1 alpha 2 beta 2 plus alpha 1 cube into beta 3. I hope this is clear. Probably you will be having a doubt in this, so you can try by writing that. So you'll get this as the cascade stage expression. So we can retain this term and we can estimate if you have all the values, or this can be further simplified into another form that is done by just squaring both sides and inverting the equation. So if I do that, it will be 1 by AIP3 square is equal to, square root will not be there, and I am just taking the inverse reciprocal. So 3 by 4 alpha 3 beta 1 plus 2 alpha 1 alpha 2 beta 2 plus alpha 1 cube into beta 3 divided by alpha 1 beta 1. Right. So this will be the equation. Now this can be further approximated as AIP3 square can be approximated by just separating it. Inside mode we cannot do that mathematically, but here I am approximating and taking it. So 3 by 4 into alpha 3 by alpha 1 plus 2 alpha 1, sorry, alpha 1 will be cancelled. So 2 alpha 2 into beta 2 by beta 1 plus alpha 1 square into beta 3 by beta 1. Right. Now further this is we are trying to take this to some other form. Now probably by looking at this you can tell that if I multiply this 3 by 4 inside, I can write this as AIP3 square as 3 by 4 alpha 3 by alpha 1 can be is nothing but alpha 1 alpha 1 and alpha 3 the ratio 4 by 3 or under root of 4 by 3 alpha 1 by alpha 3 is actually AIP3, right? So the first if I look at this first term, that represents the AIP3 of the first stage. We have two stages here. So the first stage AIP3 can be written as, so AIP3 1 can be written as 4 by 3 alpha 1 by alpha 3. Similarly, AIP3 2 can be written as under root of 4 by 3 beta 1 by beta 3. So these two things I'll bring in there. So I can write it as approximately equal to 1 by AIP3 1 square plus we'll have another term 3 by 2 alpha 2 beta 2 by beta 1, which is the term there, second term, and then you have one alpha 1 square term extra divided by AIP3 2 square. So this is this will give you another estimate of a cascaded AIP3. If you know the AIP3 of two stages individually and the values of alpha to beta 2 and beta 1. Now this equation is further we will reduce this equation by neglecting this term. We will see how can we neglect this term by looking at the spectrum, the component which is having this coefficient. So this can be neglected under some condition. We look at the spectrum and see how this this is not or this can be eliminated. If I do that, I can write this as AIP3 that is the total AIP3 of the cascaded system can be written as 1 by AIP3 1 square plus alpha 1 square divided by AIP3 2 square. So this is an approximated, or this is this formula is used as a quick reference in order to get the approximate value of AIP3 of a cascaded stage. This is what we generally use by neglecting this term, the term which is in the middle. Now this can be further extended if you have so now why I have taken second two stages in cascade is just for the reason we can actually simplify it or we can write it comfortably. Now this is generalized to any number of stages. So how will we do that is, we'll just write this expression by extending it as AIP3 square as 1 by AIP3 1 square plus alpha 1 square by AIP3 2 square plus alpha 1 square, then it is beta 1 square divided by AIP3 3 square plus etc. Then if you have a third stage, you can use some other symbol there like gamma or something, and this will be continued like this. So this will be the estimate formula to get the AIP3 of two systems in cascade, or for more systems also. You can extend that. Right. This is about estimating or arriving at a equation to estimate the IP3 AIP3 of stages when they are in cascade. This can be extended. this can be extended further. Now we have to look at the spectrum also, then only we will come to know which how these components, or how are we limiting this to only the components which are coming near to the fundamental. That we already know that if you have a system, if you have a nonlinear system, the components coming very close to the fundamental is creating issue. That is why we are looking only at the terms coming near to the fundamental. So what we'll do, yeah, since it's only, we have only less time now, what we'll do is we'll look at the spectrum of this tomorrow in the next class. So meanwhile, if you want to give a try for that, the input is given here. This is the input. So consider this input with amplitude as A. Now try the spectrum of the cascade system. So draw the components coming here, and then draw the components coming here. So when you draw the components here, you can see that I have taken the, if you look at this equation of y2 of t, in this equation of y2 of t, you can see that there are certain coefficients here, and those are the coefficient which is associated with the third order term. So plot the components at the output of y1 of t, and from those components, some components only will give you third order term at the output, right? So plot all such components and see that see the effect of each component coming at the final y2 of t at the output of the cascaded stage. So just give a try to draw the spectrum of this cascaded stage. We'll discuss that tomorrow. Right, so today I'll wind up with this, and we have 2 more classes this week, and by this week probably we'll finish unit 1 with a little more numericals. Right, so thank you for joining. Now I'll open for discussion.